Welcome to my channel. This is GeoMethod, where we turn tricky geometry into clear, simple steps. Here is today's challenge. Can you find area of the purple and green triangles? Take a moment to look at the figure and see if you can spot the idea. Then stay with me, and we will build the full solution together, one move at a time. Inside square IBCD, we want two areas: the green triangle ORC and the purple triangle ILO. The diagonal IC and the vertical line LR make the four pieces. Keep one question in the back of your mind. If this square were stretched into a rectangle with the same two given areas, would the answers change? The two white pieces are trapezoids. The right-hand one, IBRO along the right edge, has area 24. The left-hand one, LOCD along the left edge, has area 15. These fixed numbers are the only measurements we are handed, so everything must be built from them. Look first at the point O. It is exactly where the diagonal AC crosses the vertical level line LR. Because O lies on both cuts, it is the shared corner of all four pieces, so it will appear in every area equation we write. The purple triangle ILO sits in the top right corner. Its horizontal leg segment IL runs left along the top edge, and its vertical leg segment LO runs along the level line. So the corner at L is a right angle. That right angle is worth remembering, because we will lean on it for a similarity later. The green triangle ORC sits in the bottom left corner. Its vertical leg segment OR lies on the level line, and its horizontal leg segment RC runs left along the bottom edge, so the corner at R is also a right angle. Now both colored triangles are right triangles pointing into opposite corners of the square. Now use the diagonal. A diagonal of a square splits it into two congruent triangles, the right hand ABC and the left hand ACD. Each one holds exactly half of the square, so their areas are equal, and that single equality is the hinge of the whole argument. Slice the right half along the level line. The triangle IBC is made of exactly two pieces: the green triangle ORC and the 24 trapezoid IBRO. So, the right half equals the green area plus 24. Do the same to the left half. The triangle ICD is made of the purple triangle ILO and the 15 trapezoid LOCD. So the left half equals the purple area plus 15. The two halves are equal, and we wrote each of them a different way. Setting those two expressions equal gives green plus 24 equals purple plus 15. This is our first real equation linking the two unknown areas. Move green to the right and 15 to the left. 24 minus 15 is 9, so the purple area exceeds the green area by exactly 9. That is a clean first relation, but with two unknowns and one equation, we still need a second. For the second relation, the level line LR is parallel to the right and left edges, so L and R sit directly across from each other. The segments, segment IL and segment RC, are the two pieces of a full side, so segment IL plus segment RC equals the side. Compare the purple triangle ILO with the left half IDC. They share the angle at A, and both have a right angle at L and at D. Two equal angles make them similar, so purple is just a shrunken copy of the left half. In the same way, the green triangle ORC shares the angle at C with the right half IBC, and both carry a right angle at R and at B. So green is a shrunken copy of the right half. Each colored triangle is now tied to a half of the square. The scale factor of purple against the left half is segment IL over segment ID, the ratio of matching horizontal legs. The scale factor of green against the right half is segment RC over segment BC. Both segment ID and segment BC are just full sides of the square, so the two scales share the same denominator. Add the two scale factors. Over the common side, the top is segment AIL plus segment RC, which we already saw is the whole side. So the two scales add up to exactly 1. That is the fact that will close the problem. For similar figures, area grows with the square of the scale. So purple over the half equals the purple scale squared, and green over the half equals the green scale squared. Turning that around, each scale is a square root of an area ratio. Each scale is the square root of its area over the half, and the two scales sum to 1. Multiplying through by the square root of the half, the square root of purple plus the square root of green equals the square root of the half. Our second relation. Let the green area be x. Then purple is x plus 9 from the 9-unit gap, and each half is the green triangle plus the 24 trapezoid. So the half is x plus 24. Every quantity now lives in the single unknown x. Substitute those three expressions into the root relation. The square root of x plus 9 plus the square root of x equals the square root of x plus 24. This one equation carries the entire figure, and solving it pins down x. Square both sides to start removing the roots. The left side becomes x plus 9 plus twice the product of the two square roots plus x. The right side is simply x plus 24. One stubborn root still sits in that cross term. Gather the non-root terms on the left, x plus 9 plus x, into 2x plus 9. Nothing else changes yet. Now every ordinary term is tidy, and only the cross term still holds a root. Subtract 2x plus 9 from both sides. On the right, x plus 24 minus 2x minus 9 leaves 15 minus x. So, twice the root of x squared plus 9x equals 15 minus x, with the root now standing alone. Square once more to finish off the root. The left, twice a root, squares to 4 times x squared plus 9x. The right becomes 15 minus x, all squared. No roots remain from here on. Expand each side. The left is 4x squared plus 36x. The right, 15 minus x squared, is 225 minus 30x plus x squared. Now it is an ordinary polynomial equation. Move every term to the left. 4x squared minus x squared is 3x squared, 36x plus 30x is 66x, and the constant is minus 225. That gives 3x squared plus 66x minus 225 equals 0. Every coefficient is a multiple of 3, so divide through by 3. The equation shrinks to x squared plus 22x minus 75 equals 0, a clean quadratic with small whole numbers. Look for two numbers that multiply to minus 75 and add to 22, namely 25 and minus 3. So the quadratic factors as x minus 3 times x plus 25. Its roots are now visible. The roots are x equal to 3 and x equal to minus 25. A negative area is impossible, so discard minus 25. The only valid solution is x equal to 3, which is the green triangle's area. Now the purple area is x plus 9, which is 3 plus 9, so 12. Both colors are pinned down. Green is 3 and purple is 12. Check the square bookkeeping. The right half is green plus 24, so 3 plus 24 equals 27. The left half is purple plus 15, so 12 plus 15 is also 27. Therefore, the square area is 54, and both halves match. Now for the promised mystery. Was the square really essential? An affine map can stretch or shear the square into a rectangle or a parallelogram. It keeps straight lines straight, keeps ratios along the same line, and multiplies every region area by the same determinant. So the four-piece area structure survives the deformation. This is why the thumbnail question is real. In the corresponding rectangle version, with the two trapezoid areas still 15 and 24, the same area equations return. The square was the cleanest drawing, but the answer belongs to the whole affine family. Green is 3 and purple is 12. So, for the original square, the green area is 3 and the purple area is 12. And the deeper reason is not just the square shape, it is the affine area structure hidden in the diagram. And there we have it, clean and verified. If you like this video, do me a quick favor and tap the like button, then subscribe to GeoMethod so the next puzzle lands right in your feed. Have a slicker approach? Drop it in the comments. I read every one. Thanks for solving with me, and I will see you in the next one.